Can you check?
Yeah, we're live.
All right. Hello, everyone, and welcome to today's episode of Corecast. I am your host, Tim.
And I'm Mikey.
This is Sahil. Welcome, everybody, to a brand new, exciting episode of Courtcast. If you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every 5 p.m. every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode, and we'll get to it. So without further ado, let's get to it. So Tim, Mikey, this is an interesting topic. I mean, there's been a lot of rage about machine learning, AI, with the recent Nobel Prize and generally with, the advancement of large language models that people use as chatbots and all companies that have come about from that, and also its connection to physics and whatnot. So wanted to use this episode as an opportunity to explore the connection between the two, especially between something like more abstract as quantum mechanics with something that like machine learning that's like percolating through our everyday lives. So I guess Tim, I'm going to turn it over to you. Maybe you can give the audience a like high level description of what is the connection between these two. They seem unconnected. Like quantum mechanics seems to deal with small things and machine learning seems to deal with everyday things. How can they possibly be connected?
Yeah, let me just add that this connection is, by all means, is not obvious, and we don't even know if it's completely legitimate. But there have been papers that are published that uses some of the mathematics from quantum physics to maybe explore and try to understand machine learning. And the premise of the idea is simple. As we all know, quantum physics is fundamentally probabilistic. We know that in our world, things are never predictable. And the mathematics of quantum physics tells you that there are these possibilities that you sum up, and then you can calculate averages, expectations in our world. And it turns out that in statistics, you can do something very similar. If you have statistics and your data is random, you can also calculate expectations and in expectation under noise. And it is through this link, the fact that they are both random, and somehow, I would say maybe it's a little bit of kind of like a surprise miracle. It's not obvious that this works, but the math actually turns out to be very similar. So the link goes like this. First, you have quantum physics, and it turns out that if you modify the way things fluctuate a little bit, you can jump from quantum physics to thermal physics, which is the field of physics that deals with uncertainty. And if you view machine learning as kind of a sort of emergent system, like water freezing or whatever, in some sense, you can kind of think of it as a thermal system as well. As recently we also had the Nobel Prize highlighting this connection. So if you follow that leap, then you can argue that, hey, maybe, at least mathematically, some of the bits and pieces of quantum physics may be linked to machine learning.
Hey, so I don't know so much about this, but like we were talking about this before. Like, is there an analogy between this and like evolution?
What do you mean by that?
Well, I mean, like you could imagine like a machine learning when an AI model learns, you could in some situations it is analogous to like the process of evolution, right? Like if you're training a reinforcement learning agent, you could argue that learning from mistakes and it's kind of like a evolution, right? Like, is there? And I think if what you're getting at is what I think it is, like there is kind of like an analogy to, right? Because what is machine learning, right? You're looking at examples, training data, and evolving towards a certain response, right?
Yeah, I think certainly some of the language could carry. In quantum physics, we talk about states evolving, changing from one state to another. And in machine learning, you can talk about a model, a machine learning model getting trained. So in some sense, it's evolving. The question is it just I don't know, is it just a word salad, or is there something deeper to it, right? That's what we're going to explore.
I see.
Yeah. I'm excited to dig into this. So let's start off from the from the ground level. And you mentioned that there's this connection between quantum physics and thermal physics. I think that's does it go beyond just like the connection between like classical physics and quantum mechanics, where if you like go at large enough scales, you eventually get like classical behavior that emerges out of quantum mechanics, because we know things are fundamentally quantum mechanical? Or is there something like else, a different kind of connection that you're trying to establish?
Yeah, this is actually, maybe this is not well known to the layperson, but it's well known in the physics community. Like a lot of these different correspondences just like it's just approximate, right? Like you zoom in, you zoom out, you get similar behaviors. But the link between quantum physics and thermal physics is actually very, very precise. And it's almost a mathematical trick, if you like, and it's a very exact mathematical correspondence. So in previous episode we talked about the Feynman path integral formalism, that tells you in order for you to look at all the possibilities, the quantum possibilities changing and evolving, moving ebbs and flows of the wave function, how it changes, you have to sum up all the possibilities. Feynman tells you that, hey, you have to imagine a particle have to go through all possible paths and then sum them up. And then you can calculate what we call the amplitude, which links to the quantum probability of seeing something. But this is actually exactly, it's not even just analogous. This is exactly like classical probability, but with a slight modification. Like, for example, imagine you're drunk and you're just trying to get home. Like you don't know which way home is. You flip a coin. If it's heads, you move one step to the left. If it's tail, you move one step to the right, and just randomly move left and right, left and right, left and right. And where you end up, very naturally, this is the classic random walk. You sum up all the ways to get from point A to point B. You look at all the paths, sum them up using their probability. In fact, this is a lot more intuitive than quantum physics. And you literally just get the probability of reaching from point A to point B. So it turns out that there's a mathematical correspondence. The amplitude of a particle going from point A to point B, this is a quantum amplitude, an abstract quantum amplitude, is literally mathematically equivalent to the probability of a particle going on a random walk going from point A to point B, with some subtle differences that we'll discuss. So this is like a literal mathematical correspondence.
I see. So in like thermal physics, you can consider, classically, say a box of particles, and you want to ask the question, like, given this initial configuration of them, say they start off in one corner, what is the probability that they'll end up in the other corner after like some amount of time? So you examine all the different ways in which they can reach that, and eventually you'll figure out that probability. And in quantum mechanics, I mean, with far fewer particles, you imagine you want to get a particle from point A to point B, you look at all the different ways, like not only the straight line paths, but even the curvy, going backwards, going all the way to like Alpha Centauri and then back, kind of, even though that's highly unlikely, those sort of paths, and you just add them all together. So in that sense, you're drawing this analogy between the two. Is that correct?
Yeah, it's exactly correct. The only difference is, the method is literally the same in quantum physics, both in quantum physics and thermal physics, statistical physics. You look at all the possibility and you sum something up. The only difference is what is the thing that you're summing, right? In classical thermal physics, you sum up probabilities. It's very natural, right? How many ways how many ways do you have to go from left to right? Maybe you go left 5 times and go right 3 times, something like that. But in quantum physics, we don't have probability. We have something a little more abstract called the quantum amplitude. So that's the difference. On one side, you have amplitude summing up, and on the other side, you have probability summing up. But the method is exactly the same. And it turns out that even this difference, the difference between amplitude and probability, is actually just the change of one number. I guess coining a number is, it's not exactly one number, but one, you just have to change one term, and you can get one to the other.
Hey Tim, so like if I think about like temperature, like people like, you know, if I think about like thermodynamics, like at the basic level, people talk about like averages a lot. Right? Is what you're talking about something like an average in thermal physics? And if so, like what is it like an average on the quantum side? How do I think about this?
Yeah, I think it is the same. I think in some sense it is the same. But these are two.
It's like a weighted average, right?
Yeah,
almost
exactly.
like a weighted average.
Yeah. So in probability theory, you can look at the average. So one of the best example is the stock market, and this is also one of the reasons why the in the finance world they love physicists, because it turns out that all through grad school you learn all the math about particle physics, and a good chunk of it carries over to finance, and precisely for that reason, right? So for finance, you might say, oh, you know, I buy a bunch of stock. What is my expected return? You know, how much more money should I make, or should I lose something? And yeah, you sum up all the possible outcomes, and you get it. You get how much money you're gonna make. Yeah, and in quantum physics, it's kind of similar. You know, like where is my particle going to be? You can sum up kind of all the probability, but in quantum physics, we don't use probability, because particles can interfere one another. Probabilities are strictly positive. But quantum interference can be positive or negative, and in many cases even imaginary. There's a pesky little square root of -1 involved. So that is the difference. You know, in quantum physics, there is square root of -1. And in thermal physics, you only have square root of 1. You don't have square root of -1. So this is the literal difference, basically.
So I want to dig into that, because we, you know, for any listeners who have heard previous episodes, we've talked about how explicitly that quantum probabilities are not the same as classical. Yet you're here telling me that there's like, I don't know if you said an exact mathematical correspondence between the two. It's not just like approximate or not just by analogy, but actually you can transform one to the other. So maybe we can go through that and describe what is the change, and maybe give some intuition of like, how does that transformation go from like, you know, an amplitude, which is related to the probability, which is related to the quantum probability, to a classical notion of probability.
Yeah. And also, I would like to add one thing, right? In quantum mechanical calculations, a lot of times summing all these things is actually very, very hard. So what people actually do a lot of times is you pretend that you didn't have a quantum problem, and you transform your quantum problem to a thermal problem. You do your calculation, and at the end, you stick instead of 1, you stick a -1 in front of some of the numbers, and you get your answers. And you know, it's a mathematical trick, and because a lot of times the sums are not well defined in quantum physics, because you're basically, you can think of it this way: in quantum physics, in probability, probability is always between 0 and 1. You know, so like imagine I flip a coin. I flip a coin twice. What's the chance of me getting a head and a tail? You know, if I flip a coin twice, you know, there are two possible ways to do this. I can flip heads and tails, or tails and heads. So you add them up, right? But in quantum physics, the difference is that you don't just sum positive number. You have possibility, these different paths. And the amplitude, in one case, in this case, heads and tails might be +3. And tails and heads might be -1. And then you might have to add them up. And at the end of the day, you don't get a probability yet. You have to transform it and then get the probability.
Mm.
And sometimes you even get imaginary number, right? Maybe heads and tails is 1 plus square root of -1, and then tail heads is 1 minus square root of -1, and you have to add them up. You have to add these imaginary numbers up. So in that way, it's different. Hopefully, the listener understand a little bit of the details on how this works.
Yeah, I want to ask an audience question real quick. They're asking, does that mean square root of -1 is primal? I don't know if you know what that means, or.
Well, if you like algebraic number theory, you can define prime numbers also in the also with imaginary integers. So in some sense, you can think of square root of -1 as primal, but I don't want to get into details here. This is not so well.
Primal the same as prime?
Huh?
Does primal mean the same thing as prime, or are those two separate things?
Depends on what you mean. I guess in number theory, you can define a prime that cannot be factored by.
Oh, I thought I said primal. I never heard that word.
Yeah, I don't know what that means, primal. But there's a way to define prime in complex integers. But I don't want to get into like algebraic number theory, whatever that is. But
okay. You
know.
I guess what I want to ask before you go ahead, Tim, to Mikey this time, because Mikey looks super ready and pumped to answer this unknown question I'm about to ask him. Can you explain to me, Mikey, at least why classical probability and why quantum probability are not the same thing? Like, why can't I take classical probability theory naively and just apply it to quantum mechanics and why? Yeah.
Yeah, I mean, we discussed this in a previous episode, like this, like what we know as probability theory. I guess this was the argument, and I think I stand by that. Yeah, I think I stand by that. Like what we know as like probability, when you say like, oh, what's the probability that like tomorrow's going to rain, right? Like that's actually already like a coarse-grained question. Like probability, there's actually something more fundamental than a probability, which Tim alluded to, called the amplitude. So wait, the question is, why isn't there a mapping? Or
wait, like, yeah, why is there a difference? Like, what would happen if I just applied classical probability theory to quantum mechanics? Like, why do you require this amplitude business?
You would miss half the picture. Yeah, you would miss half the picture. There's got to be an analogy like this, like other than that. I don't know. It would imagine like oh, this is stupid. Imagine that like you're playing with Lego blocks your whole life, and you know that there's like, there's these types of pieces can exist. There's like the ones with the 6 joints, 6 locking joints. There's the cubes with 4. There's the angled ones. And you've been playing this with your whole life, and that's like what statisticians do with probability. They're playing with Lego blocks, and then you find out, you get a little older, and your parents tell you, "Oh, these Lego blocks, this is just like training wheels." Turns out these Lego blocks are made up of smaller joints, and you have to use those smaller bits to make up the Lego blocks that you know and love. And you'd realize that, oh, the tools that I've been using is just like a kindergarten version of the truth. What the actual building blocks are. I think it's kind of a similar way. Like, we live in this macroscopic world where things are mostly reliable, and quantum uncertainty doesn't really affect us. And so we develop these tools called probability, which allow us to make statistical inferences in the despite being subjected to ignorance about the system. And then when you learn quantum mechanics, you realize that probability is actually just a smearing of something called the amplitude, which actually has a more complicated behavior.
Yeah, I would say one manifestation of that is that probability is always positive. The more possibilities you have, you always add them up. You know, like the more ways.
It's almost like almost like you only know about positive numbers and you just discovered negative numbers. It's almost like that, right?
Yeah.
Like literally,
I think the key difference is that amplitude is allowed to go up and down. It can go negative.
Yeah.
It can even turn into an imaginary number. And this is what gives wave function is waviness. It's allowed to go up and down, left and right. And this is sort of the difference between thermophysics and quantum physics. Quantum physics is dynamical. Things can evolve up and down, left and right. And thermophysics, in contrast, gets kind of stuck. What I mean by that is thermophysics is always about thermal equilibrium. You know, we study statistical behavior of a equilibrium system usually, and when equilibrium is reached, you have statistics, but sure, the system might change, but the statistics doesn't change. So thermophysics is always about static behavior. You just have, it's like, oh, you look at a system right now. What's the probability it's A versus B? So the system has become stuck in some sense. Right, so so because of this difference between square root of -1, which allows you to undulate up and down, you have square root of 1, which is all a positive number, and this number, the only way it can do is go up and down. But of course, you know, probability, the maximum is 1, the minimum is 0, right? So in thermophysics, things tend to just decay. You know, So if you buy this link between quantum physics and thermophysics, you can kind of run a little bit of a toy experiment. So let's say you have a quantum system, and you have the analogous thermal system. You know, by just changing the quantum physics to thermophysics, and let's say you poke it with a stick. You know. In the first case, you poke the quantum system with a stick. The quantum system will respond. It will go up and down. It's like a wave coming undulating up and down because the wave evolves. But the thermal system, what it will do is first you poke it. The system will perturb a little bit. Because there's so much noise, the noise will spread out into the system. And eventually the system will just settle. So it will just turn into heat, right? It will just heat up the system a little bit, right? In the first case, the system will keep undulating, and the other case, the system will take a hit, but then the disturbances will spread out and get removed, right? So that's sort of the two key difference between the two correspondents. On one side, you have a system that's undulating. On the other side, you just have a system that if you poke it, it will dissipate basically.
And like one is reversible and the other one is not so reversible, I assume.
Yeah. And literally the mathematics, you can actually trace out how the mathematics work, and for those who are familiar with some of the equations, roughly speaking, in quantum physics, you will get something like a wave, like sines and cosines. You'll get something like sines of energy times time. You know, that's what you get, right? So it will undulate, you know. For thermal physics, you get an exponential decay. Instead of cosines, which moves up and down, you get an exponential decay. You get something like exponential negative energy divided by the temperature. So things will just decay away. So these are, if you kind of just substitute one term with another, you basically can trade the two, thermal physics and quantum physics.
Got it. So let's talk about how to make that jump, because you know we've been talking about like you need to change just one thing and then you can get this correspondence, and then maybe intuitively, as best as possible, explain like why making that one change allows you to go from a like quantum picture to a classical picture with this exact mathematical correspondence.
Yeah. Wait, can I just give a quick? I just thought of something for the less technically inclined viewers to be able to follow along. When you asked for what is the difference between like applying like probability to a quantum system. I just had this kind of thought where if you imagine like yin and yang is like it's supposed to like represent how opposites interact with each other, right?
Mm.
But imagine you couldn't see black and white. You could only see like the net, like sum of the black and the white. And you can only measure things on one scale. You can't actually see how things are like opposing each other. That would be like probability. Just seeing like the net result of the opposing interactions. Um, this amplitude object that we're talking about that has the deeper information is like seeing the full yin and yang, seeing how the cancellation of things give rise to what we call probability. I just wanted to mention that before.
Oh, fair, fair. All right, Tim, go on, go for it.
Oh yeah. So if you dig deeper to the correspondence, I think you have to look at two equations. The first is the Schrodinger equation that tells you how quantum system evolves. The second, on the other side of the coin, you have to look at Boltzmann's equation. It tells you how likely something were to occur. Those seem very different, but actually the link, that's the key of the link, right? The quantum version, it says the way the possibility moves, at least the rate of change the possibility moves, is proportional to energy, right? So that's why you see this undulation, energy times time. It undulates as energy at times time, like a wave, right? In the Boltzmann equation, on the other hand, it tells you the likelihood of seeing something is proportional to energy divided by the temperature, right? Well, actually, it's proportional to negative of that. And if you solve the equation, I mean, I'm speaking approximately, you see that the possibility of something goes down as the amount of energy that's required to keep the system there. And it makes sense because thermophysics is all about noise that's generated by fluctuation, and it's harder and harder to have more energy fluctuating. Yeah. And so that's why there's this exponential decay, right? And now you put the two together. One, you have undulation as a function of energy, right? And on the other hand, you have decay also as a function of energy. And this is exactly where the correspondence comes in. They both, the decay of probability in terms of energy and undulation in terms of energy, they both depend on the energy concept. And that is the link here, right? That is the precise link. If you just take energy out and modify that term in your theory, you can literally convert a quantum system to a thermal system.
So you're mentioning that if you're mentioning this connection between the Schrodinger equation, which and the Boltzmann equation, essentially. I mean, can you, for out of my own curiosity, can we say like the Schrodinger equation, if you make that one transformation to the time variable, you essentially get a diffusion equation? Diffusion is essential to thermal physics. Is that fair statement?
Yeah, I think that's exactly correct. And this is back in the days before people understood quantum mechanics fully. They literally used this thing called the imaginary time formalism. They just they just pretend that the time is imaginary. They stick a square root of I in it, and for those who are curious, who took a class on relativity, you know that in relativity the distance measured is distance square minus the time square, right? But if you stick a pesky imaginary number unit in front of time, you will see that, and this is kind of just numerical magic, right? But instead of distance squared minus time squared, you get distance squared plus time squared. So you kind of get the normal distance, by the Pythagorean theorem, right? So it kind of tells you that, it seems to be more than just a mathematical trick to get rid of your negative sign. But
Mhm.
in any case, minimally there is a mathematical trick for you to do it. You just flip a switch, flip the sign from negative to positive. Lo and behold, you convert quantum theory to thermal theory.
And for those of you who are very inclined to know the name of this, I believe it's called a Wick rotation, but we don't need to get more details of that. So I guess one thing I want to get intuition on is, why is it when you go to this imaginary time, do you get statistical mechanics? It seems like kind of like a happy accident. Like I don't know if you if you didn't know anything about thermal physics, like, and I told you, hey, do an imaginary time transformation, would you have been able to see, oh, this gives rise to like classical statistical mechanics, or would that yeah?
Yeah, I feel like the opinions vary.
Mm,
I think some people believe there is a deep connection, and we actually don't exactly know what the deep connection is. I think I took some classes way back, and my professor told me that it's a bit of an enigma, and maybe there's something really deep about it. Like, it's not obvious. You can just flip a sign, or change or stick an imaginary square root of -1 in, and magic happens. Or on the other hand, maybe it's just kind of a happy accident, because I know we've described something called universality, where seemingly totally different phenomenon happen to converge to the same physics. Like the wave equation, like different materials can have the same wave behavior, just because there's not that much mathematics that can describe nature. They're forced to converge. So you can hold that perspective that maybe it's just kind of a. If you think that quantum physics is something like a coarse graining, like a zooming out view of the world, and thermal physics is also kind of like a zoom out view of the world, maybe it's not crazy that they sort of converge. But I don't know. I mean, I would like to believe there's something deep. I don't know.
I
and
like the
then
universality explanation, right? Like, I don't know, this is like so like, if you have like some measured value, right? What can it do? It can grow, it can shrink, or it can oscillate. Like, what else is there really? Everything is
what
some
what
combination
about
of those things.
staying the same? I don't know. I don't know if
Well,
that's
that
reasonable.
could, well, if it stays exactly the same, that would be bizarre. But if it's just increasing monotonically, like very, very slowly, that's like, constancy is like a limit of every single one of these, whether it's oscillating with amplitude 0 or it's
Uh-huh.
growing with rate 0. Like, so
Hmm.
steady is captured in all three of these. Um, it's, yeah, like, is that related by Fourier transform to the idea that like it's like 0, infinity, or 1? Or they like, you're either growing, shrinking, or oscillating.
Yeah,
Everything's either.
I mean, you could argue that, and particularly the rate of oscillation and the rate of growth and decay is all proportional to energy. And you can argue that when you zoom
Yeah,
out a system,
yeah,
what else is
yeah,
consistent? Energy is almost
yeah.
like the de facto thing that's left over. You can argue that. But I feel like you can argue that for thermal physics. That I wouldn't disagree with you. Like, in thermal physics, what else can it depend on? It's got to be energy,
Yeah.
right?
Right.
But the weird
Hmm.
thing is quantum physics. It doesn't. It didn't have to be that way, but of course it is. Or maybe you can argue any other way quantum physics work. It wouldn't make sense. But like,
Occam's razor.
yeah.
It's right.
I don't
Extra
know.
machinery. You'd have to explain that extra machinery then.
Yeah, but I would say the 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 probability, how probability is proportional to energy and temperature,
Mm,
or 1 over the temperature. It makes sense
yeah.
intuitively, right?
Yeah.
But why quantum evolution is proportional to energy times time? That has some reason behind symmetry. It's because of Einstein's relativity. It says that space and time has to be treated on the same footing, and energy and momentum has to be treated on the same footing. And if you combine the two, you find that naturally energy times time is the right thing that goes in front of the evolution of a quantum system. I don't that's not obvious, you know. Like if the universe didn't have Einstein's symmetry, I guess it could still be true in some ways, but it feels like there's
dimension
something there.
analysis would require something like that to be true, right? The symmetry is different, the form is different, but yeah.
Yeah, kind of. But the fact that thermal physics and quantum physics uses the same energy, I don't know.
What else would it be though? It would be something up to it would probably end up being something up to a constant at most, right? Or like some convergent factor. Like I think, like you said, like there's not that many options. Like if you purport to be discovering fundamental physics, and if your goal is to find the theory of everything, when you get close to there, there's not a whole lot of ingredients to play with, right?
But I would say this. In physics, there are deep consequences because of this connection. You might argue that, oh, this is just dumb luck, right? For example, black hole temperature can be ascribed to this correspondence. You can actually, you know, there's a very slick, what we call derivation. Like, I'll loosely say how it's done, hopefully not go into too much detail. So you can look at how black hole is curved, you know. But you can, well, Einstein says black hole is curved and space and time around a black hole is curved. But you can use that equation and say, well, let me just pretend black hole has an imaginary time. Right? If you do that, it's no longer a black hole, it's completely a mathematical fantasy land. Right? But if you just say that, you say, oh, you know what, let me just pretend that black hole, the time can be imaginary. And then you look at the shape that it's describing, you see that the shape is it's not smooth. There's a singularity, but maybe that's not too surprising. But this singularity you can reach. You can actually touch it in the imaginary time. And people say, well, like, that's not good. You know, sure, you can have singularity, but if you can touch it, that's no good. The only way to get rid of that singularity is if we demand that this shape is periodic. I won't go into the details, but the crux is that you make the imaginary time a temperature, right? And this is how one of the shortest derivations of Hawking radiation comes in. You say that, hey, look, if I demand that my black hole is consistent in imaginary time, which nobody says it has to, but if I demand that it is consistent, black hole has to have a temperature. And it turns out that it's correct. So is it coincidence or is it something deep? I would like to think that there's something deep there.
Yeah, I actually thought of another thing when I first learned this that made more intuitive sense to me. So what I remember when you're computing, like, say, probability of a certain path or quantum probability of a certain path, a particle getting from point A to point B, it will, you know, most likely take the path like with the least amount of, you know, curves, at least, you know, given some nice assumptions about the environment and whatnot, which that path has the least amount of energy. And when I saw it in quantum mechanics, I mean, there's an explanation, oh, like things that wiggle around will cancel with other things that wiggle around really fast, but it still didn't really, you know, gel with me as much. But when I learned about this Wick rotation, or this going from quantum mechanics to thermal physics, you essentially get like the probability of a path for a given energy is essentially like e to the minus of that energy for some fixed temperature. So it just means that the more the path wiggles, it's exponentially decaying in probability. It's that much less likely to happen. And so it makes sense. And it gives rise to this like classical notion that the particle will take the path of, you know, least energy, or I mean, you know, with again, certain caveats, but yes. So that's one thing
You know, one can also argue that maybe there's a physical principle at play. There's a belief, I wouldn't say this is an axiom. There's a belief that the results from physics has to behave nicer than you think, right? For example, what do I mean by that? Like, for example, if you have A plus B, it's a very nice equation you can write down. Or like cosine of A plus B. It's a very nice equation to write down. But guess what? In the world of equations, there are very, very nasty equations that you can't write down in this form. And these nice equations are called, at least a part of a broader group called analytic functions. Basically, it's telling you that the function is so smooth and nicely behaved that it's better than just continuous functions. For those who study topology, you know what I mean. But these are just like nice functions like polynomials, cosines, exponentials, and things like that. If you believe that's true, then it has to be that physics, the equation, if you pretend that your arguments are imaginary numbers, it should still work. And this is the behavior behind what we call analytic continuation. So such that if you stick in an imaginary time there, or even imaginary space or imaginary energy, it's not crazy, basically. It says that, you know what, your function should still be all right. So might as well you can try to compute it. So if you believe in that principle, then it's like maybe something like that is inevitable. Like there's this, that you can generate a new, that there's this bridge because physics functions are nice, I guess.
So just to kind of state it bluntly, what we're saying essentially is that imaginary time is equivalent to 1 over the temperature. I mean, with unit conversions and whatnot, but let's just ignore that for right now. One question I have is like, we don't really fully understand like why, deep mechanistic level, why those are the same, but what are the consequences of that? It seems like I can replace a theory with time with just like just turn it into a theory with temperature. And so the states there's a link between temperature and time, but I mean inverse temperature, but you know what I mean. How can I propose that there's such a link between the two? Like, is there a link? How do you think about it?
What exactly do you mean by that? Do you mean like practical consequences? I mean,
I guess like because you've replaced a theory with time to a theory with no time but just temperature. Because in like thermal physics, I mean, there might be a notion of time, but people typically talk about temperature of a system, and then you wait for it to reach equilibrium. And I don't know, like where did the timepiece go? Like in thermal physics, I don't really see a notion of time as much, just only temperature.
Yeah. So precisely, the time in some sense is gone. Temperature is actually the length. The correspondent is 1 over temperature is like the length of time. Time here, you can think of it as different slices of your distribution that you're summing up. You can think of it that way. But time in this case is just gone, disappears, right? And as I said before, in quantum physics, it makes sense to look at the evolution of something because it undulates, right? And once you transition to a thermal theory, that part is gone. You can slice up your distribution. For those who are familiar with probability, you can look at, hey, what's the probability of having the system with this particular behavior? That kind of replaces time for you. You're just sampling the different parts of the distribution, right? You can think of it that way. But time loses meaning in this scenario, basically.
And so one other question I wanted to ask is like, in the context of this discussion, how would you characterize like quantum mechanical noise versus like statistical noise when saying that, oh, I can like do this transformation of like changing time to imaginary time, and I go from quantum amplitudes or quantum probability amplitudes to like classical probability?
Yeah, I mean, the truth is, I don't think people exactly understand quantum noise in the same way that we understand stochastic noise, because at least there's this intuition in probability theory that, oh, it could have been this way. I could have had a coin flip that's heads or tails. But in quantum physics, we don't have that. But I would say that's just...
Does noise even make sense in quantum physics based on what we've been saying? Because
it doesn't.
We're saying like noise is only when you ignore the amplitude and you project to the probability space. Then it looks like noise. But when you zoom out and look at the full yin and the yang, you see it's not noise, it's interaction almost.
Yeah,
Right?
yeah. Mhm.
Wait, I want to double click on that. That's actually that's a point I don't want to skip over. So, Mikey,
Yeah.
could you elaborate further? What do you mean by like, in quantum mechanics, noise doesn't make much sense. It's only when you project into probability, then you see noise. Like,
So
why? What does that
this is
mean?
just a thought now. This is a thought. I don't know, like, but like the way it feels to me, and I don't know.
Mhm.
My intuition tells me is like when we say noise, we mean like the unpredictability of something, right? Like
Yeah.
meaning, and it's like, oh gosh, I'm describing probability theory the way old physics professors tell you not to, as though it's like a representation of you missing some information. But I think in the way we're talking about it, it is. Because like in
Mhm.
quantum mechanics, you have this object called the amplitude. And if you have the amplitude, what you can do is you can ignore half of it and calculate the probability using the half that you didn't ignore. Um, and when we measure noise, every time we measure noise, like when a statistician says we're measuring noise, they're talking about the unpredictability that that occurs after you ignore half of the system. If you looked at the whole system, the full amplitude, there's no noise. It's deterministic. Um, but measurement outcomes based on this artificial separation of the observer and the experiment
Mhm.
force you to think about things in terms of probability, and then this
Mhm.
unpredictability in measurement comes up, which we call noise. So I might be convinced that noise is like an artifact of talking about probability,
Mhm.
ignoring the quantum effects and kind of like ignoring half of the answer and projecting onto our experiential world.
And I just want to ask, and I'll put this question out to both of you. This is like a super hypothetical, definitely not possible or far from likely. If you could have like a true God's eye view of the universe, like truly separate yourself from the universe and see it for what it is,
Yeah.
would there be? And you're just saying there'd be no noise at all. That concept would not
I
even
think
exist.
I think we did. Tim, didn't we have an episode like we argued that
Yeah,
like this God's eye view that I was talking about would be just the
yeah,
amplitude of
yeah,
the universe,
yeah.
and
I
yes,
would say
there's
so.
no
Yeah,
noise. Yeah,
yeah, yeah. I would say if you're God and you know quantum physics, God will. Imagine you flip a coin, you see heads. God will see that you are this side of the amplitude that sees heads, but God also sees all the other possibility where you
yeah,
got tails. God
Ah.
sees all possibility, but this is in contrast of ordinary statistical probability theory. If you're
Mhm.
God and you have a thermal, like if you take the thermal system literally and you flip
Mhm.
heads, God only sees heads. It doesn't see tails because you already flipped it. The heads are the tails
Mm.
are destroyed completely, and that's why no ordinary probability is that's why what we call noise is it's lossy. You lose
yeah.
information.
Mhm.
Entropy is
Lucky, a good
increasing.
word.
Like the system is almost like decaying at every moment to be just emptiness, just stochastic junk basically. And in some sense, quantum physics it has more stuff in it. And like we said,
Mhm.
there's one of the most sacred law in quantum physics, and that's
Mhm.
unitarity, the preservation of possibilities. God sees all the possibility, and they never get deleted. But when you
Mhm.
do this little mathematical trick, you replace time with imaginary time. Well, that goes away. That theorem, that preservation information goes away, so it's gone.
Oh, I mean, doesn't that violate a certain like central tenet of quantum mechanics, the so-called unitarity or conservation information? Also, shameless self-promotion to check out a past episode on
Yeah,
that.
yeah,
But
yeah,
yeah.
yeah. In thermophysics, there's no such concept. There's no analog
Mm,
of that concept, as far as I know. I think it's just completely
mm.
destroyed. I think.
In fact, it's very philosophically opposite to that.
Yeah, it's very destructive in that way. But it's just, if you think about it, it's kind of remarkable. It's just this one little term. It's just
Yeah.
square root of one versus square root of -1. That's it.
Mhm. So then how can you make that transformation in good faith because you're violating central tenet of quantum mechanics in that case. Is
I,
that not right? Or
I would just quote Feynman. This is just the shut up and calculate mantra. It just
No,
works.
no.
You know?
It's okay. Let's just shut up and calculate. But like, I think it alluded to something Tim said earlier too, where it's like if you have an equation that you think describes the universe, right? How much faith do you have in that equation? Well, let's say you know that equation works when the input is positive. Well, you want to stress
Mhm.
test it. Does it work when it's negative? You check when it's negative. You check, oh, okay, it gives the right answer when number's negative. Oh, what if
Mhm.
I make that number imaginary? Does it still hold? You could do that experiment and check if you can go to that
Oh.
regime. And so it's a testament to how the mathematics is robust,
Mhm.
despite like what you put into it. Um, and I think that's like the fact that it works, and Tim alluded to this, like surprising. It makes you feel like there's something um,
Hmm.
truthful about this.
Yeah,
Like if it only works circumstantially, right? Like maybe you wouldn't be so excited, but it's really exciting when you like stress test it, you pressure test it in places where it seems crazy, and it still gives the right answer.
yeah. I would say that there is some new emerging research topics. So if you follow some of the amplitude hedron business, I won't go into details. That and a lot of that line of thinking is, hey, maybe there's a fundamental principle about physics that the physics equations are nice to us, that we're able to stress test it. So instead of plugging in positive, instead of just plugging in positive versus negative numbers, maybe we can plug in imaginary numbers and get
Hmm.
results. And sometimes these imaginary numbers might actually give you surprising cancellations and simplification. And that's where some of these programs have made progress. It turns out that you can plug in imaginary energy, imaginary momentum, and then all of a sudden
Hmm.
your equations almost become more beautiful. But that's a
Hmm.
topic for a different time.
Very, very interesting. I want to get to two audience questions. One of them is so thermodynamics is logarithmically based. I think maybe they were possibly referring to you saying e to the minus energy over temperature or something like
Yeah,
that. I'm not
I would
exactly
say
sure.
it based on the exponential. It's because of Boltzmann's equation. It tells you that if you have a thermal system, it's exponentially less and less likely to find it with more and more energy. That's it. It's this
Mhm.
simple rule basically. So that's why probability follows an exponential decay.
Mm, okay. And then our next audience question is quantum equations have oscillation, which is sine and cosine, which themselves are in terms of these complex exponential, won't fully read it. So isn't there a connection between exponential and oscillating?
Yeah, there is, and there is. Mathematically, they're related, but also you can take Mikey's perspective, where if you believe your function is nice, in some sense,
Mm,
you can always break it down into sums of exponentials and oscillations.
Well,
So,
Fourier told us that.
right,
He
yeah,
told us that, yeah.
Fourier taught us that, and Laplace transform, right? So, yeah, I guess there is, yeah.
No, but
yeah.
I think maybe with the first question, I don't know if it's the same person because it's like a similar spheroid question. But sorry, what was the question again? In its original
The
phrase.
first one I asked, so
Yeah,
thermodynamics is logarithmically based.
yeah. I mean, well, yeah. You see logs and exponentials all over thermodynamics. Like thermodynamics is literally just logs and exponentials, and then you go to quantum field theory, and it's nothing but complex exponentials and sines and cosines. And then you realize that these two structures are mathematically identical up to a
Mhm.
change of variables. Um, so this is something that I guess we didn't mention, but it's something Tim and I were talking about before. Like, the most like nihilistic physicists just view this as a trick, right? It's like a change of
Mm,
variables. It's like integration by parts. It's like a trick you use to get the answer you want. I think that's what Tim was alluding to when he
mm,
talked about like shut up and calculate. But yeah, no, there's a large contingent of people that just think that it's like we could change the variables, like a trick you learn in high school calculus to get the answer. But that also is a testament to the fact that the mathematics is robust, independent of like, what regime it's in. So yeah.
Yeah. And then for my final question, bit loaded, I guess, does this notion break down? Does it even make sense when you bring in quantum gravity? Like, is there, I mean, I don't even know how to even ask this question, but yeah, I guess Tim, I'll point this one to you.
Yeah, I'm not sure. On the one hand, quantum gravity has this very interesting link between time and temperature, like we mentioned. Like the black hole temperature can be thought of as reliant on this link, and it gives you a hint that maybe there's more. It's more than just a mathematical trick. On the other hand, if you look at quantum gravity, maybe the notion of energy doesn't even make a lot of sense anymore. So how would you even make that link? So yeah, so very much. I really don't know, right? Like on the one hand, gravity really has some feelings of thermophysics. Like it seems thermophysics got elevated into a more fundamental role because of black holes, horizons, and all that. But on the other hand, the role of energy and time becomes more emergent. Yeah, so it's I don't know, but in any case, even if there was a correspondence, it's not the correspondence as we think of it. It might be something else
Yeah.
entirely, I think.
Yeah, I have an idea. Wait, is this the closing thoughts?
Not yet. Not yet. Almost.
Okay.
Almost. I mean, if Tim is done, we can.
Can I
I
just?
have.
I feel like this. Like I feel like my response to that is a good one.
All right. All right. Well,
Go for
in
it.
our tradition, I
Well,
want to give you guys a chance to leave the audience with any words of wisdom that
okay.
quantum mechanics and thermophysics has taught you.
Okay. I think it's highly unlikely that the introduction of gravity into quantum mechanics will require machinery that is completely different from an exponential with a real or complex argument. Like, this is apparently a good fundamental building block for almost anything you can imagine. A lot of times, it even describes things without you having to write an infinite sum of them, which is amazing. Yeah, it would be really weird if suddenly gravity makes this machinery useless. I think probably gravity will show that these basic building blocks must be assembled in a way that was so much more insanely complicated than anything anyone could have imagined, that maybe it requires an entirely new language, as like, the amplitude business is trying to do. Just literally just bypass this language and find like a simpler way to describe it that isn't as crazy. And I don't know, I was recently reminded of the Indian mathematician Ramanujan because there was a Quantum Magazine article about it, and I was just staring at some of the equations that he just like incepted out of thin air, uh, in his own words, because God told him that. Like literally, like G.J. Hardy said, he said of this of Ramanujan's work, these results must be true because if they were not true, no one could have the creativity to imagine them. And it was like these nested fractions, like just these structures, these ways of like summing things in ways that maybe we don't have like a language to describe yet, something like that. But yeah, still got to be the basic. Everything's either going up, down, oscillating, or some mix. I don't think that language is ever going to be obsolete.
Oh, is it my turn?
Yeah.
Yeah. I guess my view is that there's got to be something deeper in this connection, and I think the hint from that is because the black hole physics bit, like the fact that you can use this link, which seems like a mathematical trick, derive of all things the temperature of a black hole, right? And that's crazy to me, when I first learn of such thing. And sure, it looks like a crazy mathematical trick, but I guess in history there have been cases where many things look like just like a stupid, dumb mathematical trick. But maybe over time we will find more surprising bits out of that. And so I'm hopeful, and I know that this episode we haven't covered the whole story yet because we talk about how quantum physics linked to thermal physics, but we haven't talked about how thermal physics linked to machine learning, and we'll describe that in the next episode. And I do believe that this is sort of the general theme of science and mathematics in the upcoming century. Like, we already have a lot of great ideas. Now is the time to unify them, to borrow insights from one to explain the other. And I'm firmly in the camp that there's got to be something there. And I think if we uncover that, we're gonna see great progress. Optimistic, I'm.
Yeah, I mean, that's good that there's at least one of us that's optimistic. And so, yeah, I was about to mention we didn't at all talk about what the connection is to machine learning, but fear not, audience, we will talk about that next episode. That is our promise to you. So, yeah, on that note, I want to thank everybody for joining us, and we'll see you all next week.
All right, see you all.
Yeah.
Yeah.